nice extended weekend, whether that involved more work or more sleep or whatever it was. But if you remember, last Friday, we started reversing our process of what we had been doing prior to your test. Or for the test, we were working on starting from a rate function and trying to figure out what that tells us about how much of something there is. So we started with a rate function that was usually a curve of some sort, sometimes a straight line of either horizontal constant rate of change, or maybe a straight line going at some other angle, which still indicates rates of change are changing all the time. But from whatever sort of rate function we had, we made approximate rate functions by picking some of the values from that rate curve and used each of those values for a small interval of time in order to generate a small amount of accumulation from each rate and appended those together so that we could end up with a picture of at least a whole accumulation function. We didn't necessarily get to a nice closed form accumulation function, like come up with something like, oh, accumulation is x squared plus 2. We came up with an expression that represented how we used the rate to generate accumulation, both in that sum and an approximate form when we had delta x with intervals, and then imagining delta x shrinking down incredibly small and then expressing the same thing with an integral in order to show each rate, every single rate between a starting value designated by the problem or me and a general value of x. So any amount of accumulation starting at a, lowercase a is what we use for that, can be expressed by an integral notation representing a rate function times an incremental change in the independent variable of that rate function, which was something we picked, like a t, typically speaking, to vary between a and a general value of x, our independent variable of the overall function. So we went from rates to accumulation, and then last Friday we talked about, well, something we actually talked about a bit in chapter 4 when we were talking about Usain Bolt, how we can look at how much of something there is, in Usain Bolt's case is how far he was from the starting line, and estimate constant rates of change at various moments within that accumulation. And our goal for right now then is to take any sort of accumulation function and approximate rates of change within, lots of different moments. We're going to try to come up with a way to do this so it'll be more useful to us. We talked about on Friday, this was the curve, what the curve red F here was f of x equals x squared is shown here. This was, we talked about the area of a square accumulating as the side length grows. And we talked about, well, between side length 0 and side length 1, this first segment here goes from 0, 0 to 1, 1. The square area would be represented by x squared, and x squared between x equals 0 and x equals 1 is not something that grows at a constant rate. We know that the graph of something like x squared is a curve just from past practice, or you know that if you square numbers close to 0, they get closer, between 0 and 1, they get closer to 0. If you square 1, it stays the same, and so it must be changing at different rates. The squaring changes the inputs at different rates from how they started. So over this interval between 0 and 1, we don't actually have a constant rate of change, but this blue line segment as an accumulation graph would represent accumulation with a constant rate. Remember when you're looking at accumulation and imagining constant rates, you're imagining straight lines at whatever angle. This would be a positive rate because it's going uphill, but it's one constant rate. Like a linear function, there's one slope for this segment. So that's what we mean by, again, whenever you're looking at a graph, make sure you think carefully about what it is you're looking at. So I've got an accumulation graph here based on what we talked on Friday. Kind of skipped over the redoing the context of that. But this red curve is an exact accumulation of area in the square, and it could be total or net. We start from 0 because, well, squares have a minimum side length of 0. But this approximate accumulation gets us between 0, 0 and 1, 1. It gets us the same amount of accumulation, but just in a different way by taking one constant rate over that interval called an average rate of change, by using just the endpoints of the interval to generate that rate change in the y, dy, over change in the x, dx, or whatever the symbols, the variables might be called for a particular example. But you can see it's a different rate for the next interval that goes from 1 to 2 on the x-axis, or the coordinate points 1, 1 to 2, 4. We'd have a different rate over that second interval. And that's not a particularly accurate rate of change. You can see that the blue curve, or the blue straight lines, are definitely quite far away from the exact red curve in various places. So although we have exact accumulation and approximate accumulation, we could make a better approximate accumulation by doing what? Yeah, making delta x smaller. We can make a better approximate accumulation, and what we talked about just in general, we can make a smaller delta x. So let's pretend now that this wasn't 0, 0, 1, 1, and 2, 4. We're just zoomed in closer or something. For a general x, I can talk about this. If I'm zoomed in really close, I'm always going to see a little bit of difference unless my exact accumulation is exactly linear. But over small intervals, it's not going to be very much different. So here, let me start up this thing isn't working. Let me go back to that. So over small intervals, there's not going to be much difference. So the thing is, all we're looking for is not a way to express approximate accumulation again. We can just visualize what approximate accumulation looks like. What our goal is to write the approximate rate function and then somehow make that approximate rate function better. So for an x just within a general interval here, whatever interval this might be, left to right here, well, if these are all evenly spaced intervals, I could call this my a, but it's 0, I know. If whatever my width is, I could call this delta x and 2 delta x, or it doesn't even have to be that this is necessarily at the beginning. Imagine this anywhere in a curve. So whether it's 0 delta x and 2 delta x, or wherever it might be, however many intervals there may be to the left of this x, if I want to express that interval's left and right endpoints in general, if you remember what we talked about, just to the left of the current value of x is always the expression, well, we can express the left end of the current interval by calling it left of x. So left of x is the x value at the left end of the current interval. And that's all we're worried about. We don't have to figure out where the past interval was and where it ended or where the first interval started. To find a rate, all we need is the beginning and the end of the current interval. The beginning, we defined our left function already earlier, so we can just refer to it that way, left of x. And the right end is delta x later, so left of x plus delta x. And the y-coordinates, or the vertical dependent coordinates corresponding to those, on our exact rate of change function, red function here, f, are f of those independent variable expressions. So f of left of x and f of left of x plus delta x. So our rate function for any x that isn't dependent on this is the first interval, second interval, how wide the intervals are, what a was, I just need to know the left end of the current interval and the right end of the current interval. We don't have a function right of x. We don't need one. Just f of left of x at the left end is the y-coordinate. F of left of x plus delta x is at the right end. And if I want to find the change in the y-coordinate, I do final minus initial. So final minus initial for that numerator, final minus initial for the denominator as well, although I know exactly what that comes out to. Left of x plus delta x minus left of x is just going to leave me delta x. So in general, I can express this rate this way, and when we're done, we'd get a function that, I don't want to write the approximate accumulation function, we could write the approximate accumulation function that way, but if we just are interested in the rate function, we know what that sort of rate function is going to look like. For any value of x, I'm going to have a rate that corresponds, and there's a whole interval of x values for which the same rate corresponds. So whatever this left of x value is in this picture, from that x value through the f of x plus, no, f of left of x, no, left of x plus delta x. Too many ofs this morning. So from this, let me write that down so I don't say it backwards again. Left of x through left of x plus outside the left function, a delta x. Within that interval, all of these possible current x values would have the exact same one rate, which means our rate stays constant for a while, stays constant for delta x at a time, and if we were to graph r of x, this approximate rate function, whose definition is listed here, it would be that familiar step function that we generated last unit a lot. So we'd have one rate for a while, then a different rate for a while. For this, if this was our square again, for this first interval, we talked about what those rate values would be. 0, 0 to 1, 1, that's a rate of 1 for that first interval. And then I move on to the next interval, 1, 1 to 2, 4, that's a rate of 3 for the next interval. So 3 y's per x, there's no 3 square units of area per unit side length on average through this first interval, or the second interval there, if this was, again, back to the square in our first and second intervals. But what I want to do is take a look at kind of this general process, not just with a square, but see how you can do at generating an approximate accumulation function sketch, and then the associated rate function approximate sketch to go with it. So I've got some things. I'm going to pull up a copy of this myself. And we're going to take a look at this together.
Sure, I'll take the rest of these, I guess.
Okay, thank you. I'm going to pull up a copy of stuff here. There we go. So there's two sides to this. The side that I want you to look at first is the one that has 4 graphs on it like that. It says the big picture at the top, I believe. I know I promised a Canvas quiz in class, but I'm going to have that as part of your assignment tonight instead. I want to talk a little bit more about these. But again, at the top, big picture, thinking about what it is that we're doing right now. Make sure you always think about when you're starting, so like, all right, I'm doing math, what are we doing? All right. Big picture, right now we're working from accumulation functions to generating rate of change functions. We're going to start from, well, there's 4 blanks here. Kind of a similar question on your test, only A, it was multiple choice, and B, we were talking about the process we were doing before. But right now, we're starting from a different sort of function. What's the thing that we're starting from that you have pictured here to begin with? How would you describe this, not the shape of that curve, but what sort of thing this is? Hint, there's some words up there. We're starting from an accumulation function. Is it exact or approximate when we start? Yeah, it's exact to start with. So we're starting with an exact accumulation function. I'm going to abbreviate because otherwise this can be really messy. And then our overall goal is to get to an exact rate of change function, but we have to, exact. To go through a couple steps. So again, we're starting from this exact accumulation, and visually, we don't have to write out the function rule for it if you don't want, although we can actually do it in one line without a summation. If we write out, we can start from an exact accumulation and create an approximate accumulation, that piecewise constant, not piecewise constant, piecewise linear function. So like kind of connect the dots, create an approximate accumulation function. And once we have that approximate accumulation function that has straight line segments at different angles, different slopes, visually speaking, we can find the rate of change of each of those line segments and think about that as being, since it approximates this exact accumulation, then the rate of change of each of those segments approximates the rate of change of the actual function. So we get an approximate rate of change function, which would be our step functions. One value for a little while at a time, and eventually we can get an exact rate of change function from that. So take a look at the graphs. I'm going to leave this up there for a second, but take a look at the graphs down below. There's questions 1 and 2. Each gives you an exact accumulation function, net accumulation, in one case, and total accumulation in the other, or amount doesn't start at 0. But taking a look at those, see if you can use, as it says here, delta x, interval width of 0.2, starting at x equal to 0, or an a value, lowercase a of 0. So starting at 0 is the independent value, measure off intervals that are 0.2, 2/10 of a unit wide. Now, there's no y values on these, so don't worry about actually doing any computations, but just look at the relative sizes of things in order to first, after you've drawn the approximate accumulation, sketch roughly, without doing any computations, an approximate rate of change step function graph, and then think about what a more exact rate of change graph might look like. So take a couple minutes and just do this, connect the dots to come up with straight line segments that are the appropriate interval width, delta x equals 0.2. The x-axis is labeled, the y is not. Don't worry about the y values other than positive versus negative. Or increasing versus decreasing. Change the lighting. Sorry for the sudden, whatever. It's kind of glary in here. Maybe? No? Alright, so on this first graph, if you're using a delta x interval of 2/10, 0.2 units, then I'm going to have an interval that runs from 0 to 0.2, 0.2 to 0.4, to 0.6 to 0.8, and 1, and then the graph kind of ends, so I just stop there. But of these 1, 2, 3, 4, 5 intervals, on how many of the 5 intervals is the accumulation increasing? 3, the first 3. So the accumulation's increasing on the first 3 intervals at various rates, and on the last 2, it's decreasing, right? So if I were to sketch rate values for this, what's the difference between representing rate for sections of an accumulation that's increasing versus where it's decreasing? What happens if I'm trying to represent the rate of an increasing function, the rate of change, what quality does it have? Positive. So I'd have 3 positive rates, or 3 sections of my rate of change graph where I have positive values, and then 2 sections where I have negative. So just rough sketch-wise, I'm just going to pick a number up here. For the first interval, I'm going to have, and just doing this as we did before, with a dot on the left and an open circle or an open dot on the right. 0 to 0.2, I'll use a high positive rate, relatively speaking. And the next 2 intervals are also going to be positive, but closer to 0. So maybe the next one down here for the next 0.2. And then really quite close to 0 here and there, but a little bit positive from 0.4 to 0.6, and a little bit negative from 0.6 to 0.8, right? And then the last section here is more negative. So this is just randomly chosen. I'm not doing any computations or assuming any particular y values, but just relatively speaking, we've got 2 values for rate of change that are relatively close to 0. This hardly goes up, hardly goes down, accumulation-wise, so that means just a little bit positive and a little bit negative. But again, we use 1 constant rate for a full 0.2 units at a time, so any x value between 0 and 0.2, if I ask you what's its rate, it would correspond to this 1 rate value. The rate of change when x is between 0 and 0.2 is given by the dependent value of this rate function graph. All right, let's take a pause for just a minute. Got a special guest here to tell you about, well, we have some research that we're doing. This is my colleague Sereni, and she's got some information. So.
Thank you. You guys, there's really a lot of extras, but can you just pass them? If everyone will read this side.
Let's continue looking at rates of change and accumulations. Thank you very much for your assistance with data gathering. There's a lot of us here, so it's very helpful. So the next graph, I'll go back to the exact in a second. The next graph, if I were to do the same sort of process here, trying to think about approximate rates of change and graph think about approximate accumulations and graph approximate rates of change and accumulation. What's going to be happening with the rates throughout this graph? They all have something in common. Yeah, so this graph is all decreasing, which means our rate of change is all negative. Now, where is the rate of change of this most negative? Closest to 0 or closest to 1? X value-wise. Yeah, closest to 0. So I have larger y values here, but the rate of change is more negative between like 0 and 0.2, for instance. 0 to 0.2. The approximate accumulation graph would look like that, connect the dots. And the rate is going to be negative. But just since we don't have any y values, all we can do is kind of comparatively. This is going to be negative also, but negative closer to 0, less negative. And so on as we go across. It gets, again, slightly less negative. These 2 segments are fairly close to the same, but this one's slightly less. Just by looking at the curve itself, you can say, yeah, this should be less negative or going downhill more slowly than this one is. So my rate would be very negative maybe at the beginning for 0 through 0.2, and then less negative and a little bit less negative up through 0.6, and it just kind of continues. It's negative all along, getting slightly less negative as we go, and very hard to draw segments. But you can see it's a pretty good approximation during these later parts, a very poor approximate accumulation during the first parts. 1, 2, 3, 4, 5. Now, the directions actually said on this to do a couple other things. So in addition, like, sketch the approximate accumulation. I don't think I'd done that one on the other one quite. But the approximate accumulation function would be this kind of piecewise. And if you're doing it with something that's easier to write with than this, you can maybe even connect the dots as opposed to just having little hovering segments. But thinking about what an exact rate function might look like. First of all, how could I make a better approximate accumulation? What would I need to do? Make delta x smaller. And what would that make this approximate rate graph look like? If I make delta x smaller, I'm going to have smaller steps. I'm going to have more of them too. If I make delta x twice the size or half the size, I'm going to have twice as many intervals. So if I'm just imagining kind of what an exact rate of change would look like, it's not going to be a bunch of little steps though, even if they're really small. I could imagine making them really small and having each one just last for like, a little tiny dot almost. But if I want to make an exact rate of change, I'm going to have something that, maybe is like our exact rate of changes from last. I'm just kind of drawing something that goes from more negative to close to 0. I don't have any values here to come up with where is this precisely or where does it match up with points on here, but just something that generally starts with negative y values and becomes smoothly, because you can see this is smoothly increasing from extremely negative to less negative rate of change wise. So I should have something that isn't jumping suddenly from really negative to less negative to. If I want an exact rate of change function, it really should all connect together. So there's no reasons that looking at the pink graph those here, that the rates shouldn't just smoothly transition from one value to the next. So thinking about what our exact rate of change function actually looks like, probably some sort of smooth graph, not a bunch of chunks put together, but we're not going to get to that point using the methods we've talked about. So let me clear this off. Let me show you an animation. Let's see, this one I want. A GC thing that I've got for you. So this is a picture that you have on the other side. This graph is on the other side of your sheet of paper that we're just looking at. And right now it says h up here, but delta x as 0.4. So what this means is every time I go 0.4 forward, I'm going to think about a different interval. And for each of those intervals, I use a different rate. And so I can generate this approximate accumulation by connecting the dots every 0.4 units apart. And past the first interval here, even delta x equals 0.4 is fairly accurate. I can hardly see it on my computer screen. I doubt you can see too much gap between the straight line and the curve past x equals 0.4. But like we said, we can make the intervals smaller. Now when I do that, the delta x notation is going to go away there. But if I make it like 0.1235, because that's where it wants to stop, I can have more smaller intervals. And again, the first one still, I can see from the approximate accumulation graph that's drawn in that first interval, it's not a great approximation, but the rest of them are really close. And this rate graph that's generated from it, I can kind of see a pattern better, like, oh, going down, 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 positive, but decreasing rates, getting closer to 0 rates. Or if I make h even smaller, well, it says h up here, sorry, it's their delta x, I get more and more little steps that are shorter and shorter, each one. And again, you can hardly see the difference between the approximate accumulation and the exact accumulation, except for maybe that first interval, where the graph is extremely steep. So when it's extremely steep like that, moving over just a little bit in the x direction, our graph actually increases quite quickly and it's curved versus we need a straight line segment here. So it's going to be off there. But you can see kind of a pattern of shapes emerging just visually looking at our rate function, we have an idea of what the rates are doing, starting from high positive numbers and dropping down lower. And I can make this really, really small where it just looks like a sequence of dots. But regardless, I still have just a sequence of disconnected dots that are left to right. Each one extends for 5/1000ths of a unit in the x direction. So they're really not dots, they're really very small steps. So what we'd like to do is come up with a way to alter this process a little bit. Instead of doing the 0.4 or 0.2 and then coming up with steps of that width, what I'd like to do is generate a slightly different process where instead of having our intervals set out in the first case like 0 to 0.2, 0.2 to 0.4, and each one picking a different rate, what I want to do is pick an interval width, but every time I change x by a little bit, I'm going to change what interval is used. So kind of the idea of, if you remember when we were trying to get our exact accumulation before, we talked about, well, if we make the delta x extremely small, this isn't quite that, but if we make the delta x extremely small, every time I move x a little bit, I'm in a new interval. I want kind of that idea, but more so even than that. Here, let me pause this for a minute. I'm going to make our delta x large again. But instead of having, what I want to do, instead of having fixed interval widths that have a specific beginning and ending point and keeping one x value for a while, regardless of how long that for a while is, if it's a little while or a long while, what I want to do is every time I change x, even the smallest bit, even less than 0.000005, I want to have a new interval to use, and not necessarily calculating an average rate of change over a minuscule interval, but just picking a normal size interval like 0.4, which we can see, and instead thinking about, let me get this playing again, moving the interval, instead of with delta x, how we had this, like it was just fixed 0.4 units at a time. Every time I move x, what I'm going to do, instead of generating this accumulation function the way that the pink is shown there, which is what we did before with delta x equals 0.4, what I want to do is move the interval along with x. So I have a smoothly moving interval to use. And every time I look at x, I'm looking at whatever distance. I'm using 0.4 here, which is still going to give me an approximation. But it's an approximation that doesn't keep one rate value for a while. Every time I change x values, oops, I think I skipped over one. Every time I change x values, I'm going to change what interval I'm finding that average rate of change over. So even the smallest amount of change in x with a visibly large h here, I'm using h now instead of delta x just to distinguish the two processes. Using delta x like we did with our sum, we can set those positions on the x-axis out in advance. This h, I'm just going to imagine as a distance that I look in front of x, in front of the current value of x, in order to make an interval over which I'm generating an average rate. So what this means then is, every time I change x a little, the rate changes a little. Let me scoot this back a little bit. So what I'm doing is when x is here, that's the interval I'm using. When x is, this looks like it's about 0.2, it's like 0.22. So if this is an h value, this sliding interval width of 0.4, this goes from x equals 0.22 to x equals 0.62. And if I move x just a little bit, now it's x equals 0.25 to x equals 0.65. Every time I shuffle x or scoot x just a little bit or imagine a slightly different value of x, I have a slightly different interval that I'm measuring the rate of change over. And so you can see what happens to this rate function. Instead of generating x rate values that I use for a while, the rate values are always changing when in the accumulation the rate function is actually changing. When the rate of change changes over here, when it becomes, as this one does, less positive, this instantly recognizes, oh, I'm becoming less positive, not by jumping to a new segment, but instead by decreasing from the previous one. Because I could always decrease, less. Now with this, I have a limitation on how precise I can scoot just a little bit. But the graph on the right, it's really hard to, I can't graph all of the pieces of the approximate accumulation at the same time because each of them there'd be infinitely many secant lines like this, infinitely many lines, one then another, then another, then another. It'd look like a crazy like art project with all these different lines intersecting one another by the time I'm done. So I'm only showing one. This is an approximate accumulation that we're using right when x is 0. When x is slightly bigger than 0, I'm using this approximate accumulation, and this is just the smallest amount of nudging that I can give my x here. But every time I increase x by a little bit, I get a slightly different rate, and each rate blends into the next rate, because as I can see, this accumulation function in the right graph doesn't suddenly change. It doesn't have any of those rate of change in a moment doesn't exist sort of vertex points where it suddenly changes from positive to negative or from one value to a different value by jumping. Looking at this, I'd say I've got large positive rates followed by smaller and smaller positive rates. So I'd expect my rate function to look something like this if it's exact. Now this isn't exact. Why is this blue graph on the left for rate not an exact rate of change function? Maybe think about what was going on at the beginning. It's not an exact rate of change function. If you see what's going on the right, when x is this small value of 0.06, I can see that the rate that's calculated isn't actually what's going on at x equals 0.06. If I look closer in to the moment where x is 0.06, I would see a rate that's higher than the rate indicated by this blue line. So it's still an approximate rate function. It's just a different sort of approximate rate function from what we had before. So the method we used on the front side of this, of the sheet with the two different graphs, is generating an approximate rate function one separate interval at a time. And intervals that are adjacent to one another, they don't overlap at all. And we pick one rate for each interval. Or as x stays within one interval, the rate of change stays constant for a little while. But there's no fixed intervals here. I'm just using a particular interval width. And so I used a larger one so we can visualize this, but I could make a smaller sliding interval here and get something that more closely represents. You can see what happens to the rate function. When I use this large interval, that blue diagonal line there on the right, as compared to the rate function it shows on the left, the dot at the end represents the rate right now, which looks like about 8. Well, if I make this interval narrower, it'll more closely represent the rate of change that's happening at this x equals 0.06. If I make the interval narrower, this is more close to what's going on around x equals 0.06. I can't see a gap anymore. This is with h equals 0.0366. And notice this rate of change is a lot larger a number now. So it was a poor approximation, better approximation. But regardless, let me animate this and do that. If I have a larger h interval or a smaller h interval that moves along with x, regardless of whether it's large or small, I do get a connected or a continuous rate graph that decreases smoothly instead of in chunks. And so what happens if I make the interval for h, this where do I calculate this average rate of change, if I make it smaller, it doesn't change the type of graph that I have, it just changes a little bit the shape. So let me put this across. So when I have a larger h value, this is a more approximate rate graph you can see on the left. If I make this h, or the interval length, smaller, I've got generally the same sort of graph. I've got different values, but the smaller h is, the more close to exact this rate of change graph is going to be. And the idea is there is this magical exact rate of change that we're headed towards. Approximate, getting closer and closer to exact. And what we're going to talk about next class period is how to algebraically come up with an actual closed form expression, like a normal looking f of x equals like x squared plus 7 sort of formula for exact rates in a couple of cases. And that's what our task is going to be for the next several weeks, to figure out how to do that for any rate function or any accumulation function to find its rate. All right, so that's it for today. Take a look at what's on the rest of this sheet. We're going to discuss some of the details down below. And there will be a Canvas quiz tonight related to your reading and these two different methods or approaches. But that's coming up later. Yes.
Is there a written quiz on that?
Is there a, it'll be a take home. Yeah. So I'll talk about that in the assignments tonight, but yeah.